Okay, I mean, okay, it's basically now about parallel HDF5. So it's basically quite straightforward to implement this if you're already and if you write your I/O using HDF5. You have to add some additional functions to let basically the function know that you want to use parallel I/O and the MPI-IO backup. Basically, you have to specify a parallel file driver by giving it the MPI communicator and its structure to create a file access property that the MPI-IO file driver is aware that you want to use it. Basically, you can do this with this function h5pset f appl MPI, where basically you give here the MPI, the MPI communicator and the MPI info structure to this function. And then you create a file handle which is aware of that you want to, yeah. Then you create basically then you create a file, and then you can use it afterwards to do parallel I/O. So this is basically the function which you have to call. So this is what I already showed. There, this communicator is the MPI communicator, and this info is the MPI info. So I basically have this in this. Which one? This one? Yes, I have this in this example file. So if you take a look to the exercise or this x2 file, then you see this basically. So let's copy this to the local directory. Copy it to the path has to be correct. So now we have this exercise 2 here, where you see basically that that this function is called basically here. Where you give this this handle from h5p create to it, and then you can basically so the MPI-IO file driver can be also set to collective mode to enable collective bufferings, which is not so basically one can do this by sorry, by use this function h5pset dxpl MPI-IO, where you specify what kind of MPI-IO function you want to use. So here you use this collective call. So this is a function that sets their data transfer property lists to the transfer mode, which is the second handle here. And the modes which are basically available are, which is just use, which is CCI, H5, FD, MPI-O independent, and MPI collective. So with this, basically, you use this collective I/O. Then you basically need to tell the different MPI tasks in which position you need to write the files. So that basically you have to set the offset, which you can do with this function h5sselect hyperslab. So basically, if you want to write a one-dimensional data array, you need to say, okay, task 0, please start at position 0. Task 1, please start to write at position yeah, after the space where task 0 is writing. So for this you can basically set with this function hyperselect select hyperselect. So basically here the offset is given by in this one-dimensional. If you want to write an n-dimensional array, the number of numbers locally stored times your rank. So this would be the offset. In a 2- and 3-dimensional, you have to, I mean, you can do something like a lexicographical index to set these offsets. And then you give basically, you use the same function to write your data like you did in the serial applications, only that you now give this transfer handle to the function which you generated at this point here. Sorry, my voice is. I mean, which you basically where you add the information that you want to do MPI-IO collective with this function. You need to give to H5D right that this function knows, okay, that use now this MPI-IO collective transfer method to write your data. Yeah, so this is in principle how you create this parallel I/O in which HDF5. So what you need basically is you need to create this handle which knows about your communicator, and then you need to basically you need to tell the function which kind of transfer model you want to use, and you need to give the offsets. So, and the offsets can be depends then really on the different ranks, and you don't want to write data, and you don't want that that MPI tasks are battling around for writing the data. So, okay, let's run this, and then we can profile this and take a look how this looks like if we take a look using scope P. So for this you have to be really careful because the MPI libraries are not the same. There can be some issues with the versioning. At least it was working. So let's allocate a node again. This is alloc. And run this. In this case, it's generated this in my parallel .h5 like it is here. I mean, what this function is basically doing, it's writing out this kind of data here. So let's take a look to my parallel H5, how this looks like. So there's a data set now with 16 float numbers. So each of these 4 processes was writing 4 floats. Let's take a look. This one is D, and then data set 0. Where you see that I mean, the first process wrote 0, 1, 2, 3. The second wrote 4, 5, 6, 7, and so on. So, for example, if you now run this with 10 jobs, the data set is longer, so consists of 40 floats. So if we, for example, now increase a bit the size, then we can take a look to the profiler how this looks there. No, it's a bit, it's a C code, so it takes a while. Let's count now. Compiling this again. And running it with 40 jobs. Are there questions so far? Or some remarks? Okay, so now this is, I think, a bit larger. Let's see, let's have a look. Okay, not really much larger, 14 kilobytes. Okay. No, I just download the profiling data to take a look how this looks like. If you don't give a correct, I mean, if you don't give it folder, then it just gives you the timestamp. So you see basically April the 21st at 15. It's 3 o'clock 50. No. Okay, basically, okay, now you see that the provider recognized that there were some I/O, because this I/O here, actually there were some bytes, and it was using MPI-IO, as you can see here. Okay, and okay, the file itself, you see that basically it doesn't really see the HDF5 functions. Here you just see the underlying MPI function. So HDF5 is calling MPI-IO functions. Basically this MPI file write at all, which is writing down the data sets. So you see this basically also then here that, yeah, okay, this is here now. It has to select this so that each of these, you see that each of these rank were written 3,200 bytes of I/O. Good. Okay. Okay, now we can basically, I mean, what is now important, it depends a bit on your data structure, what you want to write out. So there may be different cases. I mean, what is basically now more difficult in the application is basically I mean, what is now basically important, or what is maybe critical in the application is to set really the offsets that each of their that each MPI task is writing to the right point in the file. And for this, basically, yeah, here's one example giving a three-dimensional grid, which is balanced partitioned. You just use basically the lexicographical index for setting these offsets. As I said, this kind of offsets depends on the rank which you give in. You give the rank. Yeah, in H5S create simple, you give the rank of your data structure or the dimension of the data structure, and if it's in this case maybe 3-dimensional, these variables are pointers to 3 variables. So if you want to write this 3-dimensional data, you give basically offsets. You can give offsets in this 3-dimension, basically shown here. So this function would then give take a 3-dimensional pointer to the pointer to an array of with 3 entries. Okay, so okay, this is just an overview what parallel I/O can do, and basically at the end of what I wanted to discuss today. So maybe I'll just give you the small the last slide about the conclusion, and then we can, if you have questions or remarks or whatever, we can discuss this. So basically, as I already said during the session, we have a hackathon coming up in 1 month. It's basically on the 17th of May to the 21st of May. And we're still looking for projects which we can work with basically ones which want to apply this on our HPC infrastructure. Basically, we will help them and support them to scale this up and to speed this up and to optimize this on our facility. And we also have an academic and industry call for high-level support. So if you need high-level support, take a look to our website. There's a form which you can fill that you can, according to that, you can provide them help in porting or whatever. Okay, so yeah, thanks for participating today. And as I said, I think we can discuss questions, or we can provide something else as you want.
Okay, so you're done, Jakob, as I understand?
Yeah, basically, yes. I mean,
okay. Well, thank you, Jakob, for all your time and your knowledge. For those people that are still online, if you can please provide us with feedback for today. I've put this on Slack, and I'm putting it on now. I'll put it on the Zoom, a link to our feedback form, just so we know what we need to include in future events and such. These recordings are online and will be online soon. Whenever Jakob sends me and Simona the presentation, those will also be online. So yeah, as Jakob said, we're going to have a call for the participation to the hackathon soon. Hopefully we can send this to you next week. We just need to finalize a few details. And yeah, you can attend the hackathon in a number of ways. Those will be detailed in the announcement. So if there's nothing more, which I think there isn't because there's not many people left, then we can end for today. Thank you all for joining, and thanks to our trainers Yannis, Simona and Jakob today, and hope to see you in our future events, whether that's seminars or hackathon next month or training events later on. Can you ask a few questions after you close the recording? I will close it now, and you can ask Maria, yes.